Our next goal is to use what we've learned to try to figure out a formula for the volume of a sphere. At the moment, we know how to find the volume of cylinders, which is pi r squared times their height. We know how to find the volume of cones, which is pi r squared times the height times 1/3, because a cone takes up 1/3 the volume of its corresponding cylinder. What we're going to do is we're going to try to use these two pieces of information to figure out the volume of a hemisphere. A hemisphere being half of a sphere, the same way that the northern hemisphere is half of the planet Earth. The way we're going to combine the piece of information we know into something we don't is by using something called Cavalieri's principle. Cavalieri's principle says that if you have two figures that have the same cross-sectional area at any slice you take, then the two solids will have to have the same volume. The key conditions are that, one, the solids have to be the same height. And secondly, they have to have the same cross-sectional area at any height. If we have both of these factors in play, then these solids have to have the same volume. So what we're going to do is we're going to show that at any height h of these figures, the cross-sectional area of the cylinder minus the cross-sectional area of the cone at that same height h is equal to the cross-sectional area of the hemisphere. For any of our heights h, that should work. To make our lives easier, we're going to pick a very special set of cylinders, cones, and hemispheres. We're going to make all of them have the same radius r. Now, because this is a sphere, any point on it is going to be the same distance away from the center, which means this sphere has a height of r, and so in order to use Cavalieri's principle, all of our figures have to have the same height. So we're going to be looking at a cone whose height is the same as its radius, and a cylinder whose height is the same as its radius. So all of my figures have a radius of capital R and a height of capital R, and we're going to be looking at the cross-sections at any given height h above the ground. Let's start with the easy one, the cylinder. What does the cylinder's cross-section look like at height h above the ground? Well, it's a cylinder, which means it's a lot like a prism. All of its cross-sections are going to be congruent to its two bases. The area of its cross-section is just going to be pi capital R squared, the radius of the large circle. Okay, that was straightforward. What about the cone? The cone doesn't have the same radius going all the way up. This means that the area of its cross-section does depend on the value of h. We know that overall it has a height of r and a radius of r. But I don't know what this tiny radius is. I'll use a lowercase r to represent the radius of the actual cross-section. So we have to ask ourselves, well, what do we know about this cone? Well, if I'm looking at it from the side, the cone's profile forms a triangle that has a radius of big R and a height of big R. Any cone that gets filled up partially along the way is going to be similar to the overall cone. So if I have a tiny cone here that is filled up to height h, it should have the same relative properties as the big cone. Well, the big cone has the property that its radius is equal to its height, which means my small cone should also have that same property. This radius is equal to its height, the same way that the radius of the entire cone should be equal to its height. This means that the area of any of the cross-sectional slices, which would normally be pi r squared, can instead be written as pi h squared. However high above the ground you are, that's what your radius is. If we're all the way at the point where our height is 0, our radius is also 0. If we're at the full top of the cone where our height is a capital R, our radius should also be a capital R. So anywhere in between the two, the radius should always be equal to the height. Now for the tricksy part. The hemisphere. Once again, we are taking a slice at h units above the ground. Once again, that slice is a circle. And once again, we are trying to figure out what on earth is the radius of this circle, this little lowercase r. Well, think about it this way. If this is a broken down diagram of the situation here, I know that we are h units above the ground, and I know that we have a radius of some unknown length r. Do I know what this distance is? Yes, I do. This is a sphere. Well, it's half of a sphere. For a hemisphere, all the points that are on the hemisphere are the same distance away from the center. This is a point on the hemisphere. This is the center from which this line is being drawn to. If this is a point on the hemisphere, and this hemisphere has a radius of r, then this point has to be r units away from the center. Oh my goodness, it's a right triangle. I don't know what r is, but I know that h squared plus little r squared should equal the radius of the entire sphere. That means I can express this unknown r value in terms of the two things I'm given, the radius of the sphere and the height we are above the ground. This means that the area of this cross-section, which was pi r squared, can now be written as pi times r squared minus h squared. So we have found the cross-sectional areas for each of these three shapes. And lo and behold, it does fulfill this original equation that we were talking about up here. Does the volume of a cylinder at each slice, these are all the slices, these are all area of slices. So does the cylinder slice minus the cone slice equal the sphere slice at every h? Well, yes, they do. The cylinder slice has an area of pi capital R squared. The cone slice has an area of pi times however high above the ground you are squared. Does that equal pi times r squared minus h squared? It most certainly does. If I distribute this pi to these two terms, I get two equivalent statements. So I know that Cavalieri's principle is in play here. All these figures are the same height, and they have the same cross-sections at any given height h, which means I can express the volume of this hemisphere that I don't know in terms of the volume of these two figures, which I do. So in other words, V cylinder minus V cone equals V hemisphere. Volume of cylinder is pi r squared h, use a capital R here, minus 1/3 pi r squared h equals V hemisphere. Combine these things together because they're both a fraction of pi r squared h's. I'm left with 2/3 pi r squared h, which is the volume of a hemisphere. However, we're going for the volume of a sphere, a full one. I know that a hemisphere is 1/2 of a sphere. Therefore, the volume of a sphere should equal 2 times the volume of a hemisphere. Therefore, the sphere should be 2 times 2/3 pi r cubed. Therefore, really big therefore, the volume of a sphere is 4/3 pi r cubed. To find the volume of a sphere, take its radius, multiply it by itself 3 times, multiply that by pi, multiply that by 4/3. The volume of a sphere is 4/3 pi r cubed.